All right, welcome everybody. Let's start off with homework questions. Who of you have questions about homework? Yes. Yeah, a lot of getting your data ready is by just putting in the format and data, and then CSV is probably the most common.
How do you want to go about measuring like the performance of our model?
So time is the number one thing to record about how long it takes to, in this case, just predict, because there is no training, right? So time is the only thing. Time IT is one thing that some people are reusing to record how long it goes from one step in Python to another step. Now, the other feature to talk about is how many data points did it process? Processing 1 million data points is much different than processing, a few thousand. Now, in the future, we will also talk about training time. And we will also talk about things like how many, how much computation was actually done. If you use something like Python multiprocessing and you're running on 16 cores instead of just one, then the time, it means something else, right? There's something else going on. And what you'll find is that processing something on 16 cores instead of one core does not make it 16 times faster. Why would that be? Source allocation. What does that mean? Like, what's going on?
Effectively split up at 16. So it's not 16 times faster.
Even if you could split it up into 16 perfectly, why would it still not be 1/16th time? The splitting up part takes time too. And what often happens is when you're programming, there's a lot going on behind the scenes. And Python notebooks, Jupyter or Colab, there's an extra layer of stuff in between you and the actual code. So let's not talk about that. Let's just talk for a second about if you're running something on the command line. You have a Python interpreter going through your code. And first of all, it goes through your code more than once. The first time it goes through just to load the modules that it knows are needed. And it may find syntax errors. Then the next time it actually is running things. And let's say it's running things and it gets to, there's this thing called multiprocessing. This is a brand new marker. Technology, this isn't what it used to be. All right. Multiprocessing has this thing called pool. So you might have this one section where you say, with pool, et cetera, you have some things run here. And let's say you chose it to use 16 processors. Then it takes everything that was in the stack. Who knows what the stack is? I saw a hand raised, no? What's the stack?
It's just like the stack of calculations.
Yeah. Yeah, and it's kind of the state of everything Python needs to know to execute the next part of your computation. Now, sometimes what it needs to know are variables, the states of variables, and all that stuff. And for Python multiprocessing to work, that's the name of this module that allows you to do things on multiple cores. Everything that it needs to share to those other processors has to be serializable. Who knows what that means? Serializable. You kind of have the right idea. So if you have a Python dict, okay? And let's say it was something like this. You have some variable and it has a value. You have some, these are keys, like some other key, we'll call it key 2, and it has another value. This dict can be serialized. Anything that can be JSONified usually can be serialized. Turned from this thing, which actually doesn't have a prescribed order. A dict can be in any order, as long as this is associated with that. But this thing gets be put into a serial format where it's one thing after another, one character after another. So anything that can be JSONified, especially with the Python JSON module, can be serialized and therefore can be shared amongst cores when you're running it in multi-processing. Now, you guys can come back to this part of the lecture when you see it on video. Has Caleb, the TA, interacted with any of you yet on email? You all know his email though, right? It's on the syllabus if you need it. He's the one who will eventually, he told me very soon, be posting the videos of all these, the recordings that we already have, the last two, today's the 3rd. Okay, so just to recap, when you're running something in parallel, then you want to make sure that the important objects being shared are not giant custom objects, but instead things that are serializable. You know, dicts and lists, arrays, things like that. And that will affect how you report performance. Performance, go ahead.
I guess my question is also, you just wanted to measure the predict method.
Yes. No. Just predict method. And it's kind of a game right now because obviously it's doing nothing, but I want to get you into some habits so that when we go on and make our real models, starting this week on Thursday, then you will already be thinking about these things. Now, is there anybody who has tried to use Google Colab and has not been able to? 1, 2, 3, 4, and I already knew about you. We found a workaround and there's more than one answer. So apparently, Google Colab is free to all Google accounts in the world except for Gonzaga. That I've heard of so far. So solution number 1 is use your personal Google account. Because remember, it's free to everyone in the world, except for your Gonzaga.edu account. Second solution is use Jupyter install. Just install Jupyter on your laptop or your computer or anywhere. And then the resulting .ipnyb file, copy and paste that into the Google folder.
Where we put our CSV file?
You would have to copy that into.
If we do that, how can we be sure that like the modules we get supported are working? Or are they just
Yeah.
always?
No, they might not. You're right, they might not run. But the IPNYB file should have the state of all the cells. But if it doesn't, you know what you might need to do? Print your output to a separate file. So if you don't do number 1, if you do number 2, you might have to copy in an output file that has the actual output. It could be output.csv or .json or .text. Any of those works for the output file. Okay. Now let's jump back into where we were with just a little bit of recap. Conventional programming, you got a person programming the computer on what to do. Machine learning is where you program a computer to program itself, to teach itself what to do. I want everybody to feel excited about asking questions if anything here feels unclear. Okay. Who can give me the intuition that I was trying to give you for information? What is the intuition?
More aware, something is more valuable.
Very good. That's perfect. You guys got it. Okay, we talked about old speech recognition. Well, there is this moment in the early 2000s where we finally hit 96% accuracy. Now, it depends which context, which accent. There's a lot of things. But there were a few companies out there that finally hit 96% accuracy on some of their measures when texting on your phone. When you hit that little button, say I'm going to talk to my phone, I'm going to text it or whatever, but that moment we hit 96 and went from annoying, mildly annoying to everybody started. That was the tipping point. And since then, I found that to kind of be a broad tipping point. When any machine learning system hits 96% accuracy, everyone feels like, yeah, I'll probably use this all the time. And the errors, 6% errors, becomes a mild annoyance that you really can't. Think about it as a tax. That happened after deep learning. It didn't happen before. So I was at Nuance from 2003 to 2008. And during that time, we were still using the old statistical method, the one we talked about last time, with all those fancy Fourier transforms and all this stuff. In fact, we had many layers of models. Each one depended on the one below. Like, at the bottom, the lowest layer, we had the acoustic model. This model would look at the actual waveforms and the spectrograms we talked about last time, whether they had 45 dimensions for each little contextual phoneme or others, depending on the year. But the acoustic model would turn that all into a bunch of potential phonemes. So going from the actual waves to phonemes. Like, you remember this example about Sunday, Monday, Tuesday. That didn't match better than Sunday, Monday, Tuesday, but you had to have both options, Sunday. In fact, for every little thing we had in here, every little possible phoneme, we would have multiple options. And multiple options for every one of these means combinatorically, there would be a mind-blowing number of possible sentences this person could be saying. So we had to find ways to manage all the complexity of matching each one of these. And we came up, well, what was common, not just at our company, but at various other companies, was having something called, we called it, I don't remember who coined the term, but beam search. So you're searching the space of possible combinations of phonemes for the most likely one to have made the observed data. Maximum likelihood estimation was another way to say it, or just maximum likelihood. And beam search meant that within just this phonemes model, we're going to not consider all possibilities. We're going to consider some. And it's not a width of 1, it's a width of maybe 5 or 7 or 9. That's our beam. And let's say we're also tracking how many possible combinations there are. And after these two, there's going to be 3 times 3. That's 6. We got 6 now. I had another one here. It's still 6. But if we get to this one, let's say D and T are both possible. So now it's 12. So let's say we set our beam to be 10. And now 12 is higher. So we're going to cut off a couple possibilities. And we cut off some that are lower probability. Like maybe this one was, had a smaller probability. So now that possibility path is cut off. And now we're down to 3 times 2 is 5 times 2. Now we're down to 10. So that would be the kind of thing we would do. And as the program would run, it would know what hardware it's on, and it would tune the size of this beam to be appropriate to that hardware so that it would all respond. It would finish the entire process within a certain number of seconds. Now, above the phonemes model, we had the language model. Now, the word language model can mean different things, different years, and to different people. Really, it's a statistical model of word combinations. And there are some word combinations that, given the beginning, you know what the next word is going to be. What would the next word almost always be in English? Yes. You've learned that implicitly just from being alive and hearing a lot, reading a lot. Well, it turns out that what's going on here is other words are possible. If someone said raining cats and giraffes, you would still understand what they said. And you wouldn't, have a panic attack, for example. But it's very, very unlikely. And in fact, me saying it right now, this may have been the first time it was uttered since the history of the world. And statistically speaking, every day, every one of you utters at least one sentence that has never been uttered, which is kind of amazing. But this language model's job is to do for words what we were doing for phonemes here. So let's say it maybe thinks your first word is Sunday, but the second probable word might be Monday. And over here, maybe the second possible word is or was, or maybe it's as. So you're starting to build up possible sentences based on these combinations. And in the same way we did beam search here, and we limited the number of possible word combinations we were going to keep in memory. We're doing this for here, we're doing this here, and we're kind of doing it in here too. So we're doing this in multiple layers all at once. And I knew the guy who was in charge of setting the thresholds for all of these. Like, at what exact, probability or accuracy do you drop off possibility chains in this circumstance, in that circumstance, on this hardware, on that hardware? It was a full-time job for a guy with a PhD and 20 years of experience. setting all those full-time job. With neural networks, you don't have to do any of that. You just let the system figure it all out for itself. Have you ever heard someone say that this model was trained end to end? What that means in this case is you have on one end a sound file, and on the other end, the fully recognized string of text. Maybe even the grammar has been, corrected or normalized. A system that can go from one end to the other is called end to end, and is trained end to end, where the supervision only happens at the end. Now, the problem is, you don't know what's going on in the middle, and maybe these systems are getting to the right answer for the wrong reasons. You don't know that, and you might never know that. Anyway, when I was at Nuance, one day they were talking about Google 411. What you guys don't remember is that in the old days, if you wanted a phone number, like a company or whatever, you had to pay 25 cents just to look up a phone number on the phone. And there was no online. But you would call 411. You've all heard of 411, right? Who's ever used it? Well, give me the 411 means give me the information, right? That comes from the old days. You would dial 411, say, Bob Pizza downtown, and then the phone number. Then you could get off the phone and call Bob Pizza. That cost you 25 cents every time you did it. So Google came up with this thing. You just call 800 Goog 411. And instead of asking a human and paying 25 cents, it was free. And you would say the number, but it wasn't a human who was answering you. It was voice recognition. It would understand what you said and then give you the answer. And it would be an automatic speech attendant who would speak back the answer to you. And they would get it from their own Google servers, of course. Now, the one piece Google did not have, they didn't have their own speech to text. So they're using Nuance. And they gave Nuance a bunch of extra money, so they Google it. And I remember hearing about this. That might not be a wise decision. Pretty much within a few years, Google had all this data, and they trained their deep learning systems. People weren't using deep learning. And then pretty much they took over. They were the first ones, at least on Android, to have one that actually worked, that worked well, that reached 96% accuracy, and then everybody started using it, and it became ubiquitous and normal, and I can even do it on my TV now. Are there any of you that do not regularly use speech? Why not?
I just don't have it. I can't speak easily, like I'm in a setting where it's not good to talk out loud, or I'm just fighting. Actually,
If you had Neuralink,
as in,
the brain thing.
and that's true. You just think it.
Yeah.
I feel like it's a little bit bigger because I have to think it in the type or think it and say it that I was thinking.
Yeah. If you had that, you could use that. Probably. Who else doesn't use speech text? Why?
I'm just stuck in my ways, stubborn.
You're an old man?
Yeah, I'm alright. I'm alright.
Yeah. I don't use it. I'm very consistent. I use it all the time. It's just text. It's stay wrong. All right. What do you want? Interesting. I feel like if it's just sending a message sometimes, but if I'm working an essay or something, I feel like you think you're going to say something rather than write. So when someone's speaking, they usually speak maybe 100 words a minute. Only the best typers in the world on 2 hands can type. So the fact that it's slower doesn't seem to bother you. I think. Also, how many of you hit the actual characters one at a time versus swiping? How many of you swipe? Only 4 of us. Sometimes it. The rest of you, you hit each letter one at a time. You guys have a lot of time there. Huh? And you use your, how many use your thumb? 2 thumbs? Okay, so at least you're doing 2 at the same time. How many use an index finger? Only me? I'm the only one, but at least I swipe, so I'm probably faster than any of you guys. You did notice that, yes.
How is Google doing that call to get a number thing if it already exists? Wasn't there technology people were able to pick it up?
No, but maybe, I mean, if you could go to the, library or go home and log on to AOL by calling the phone number and all that stupid stuff, whatever, then you could do a Google search. But this is for people who only wanted to use their phone. Maybe they're out and about and they have their cell phone that literally does not have internet on it. Before that, they would call in and then their voice, whatever they said, would go to Google. Google would take part of the voice call, just the part that they thought was you saying the name of the business. They would send that as an utterance file to Nuance servers. Nuance would send back the text, just the text. This is an utterance. And this text would be the name of the business or the name of whatever you said. If you said something totally wrong, then that would be what goes into the Google search. And Google would do their own search on their own systems for company listings. It didn't work for people names. It was only company listings. And then they would get the results, and that would go into the opposite of speech to text, text to speech. And then they would play that back to you on the phone. Now, the reason this was such a great thing for Google was that they would also ask you, would you like to be connected? So you wouldn't have to make a separate call. They would just pass you along. Now that costs money to them because they're keeping their own phone line open and they are potentially even making a long distance call. But if you said yes, what does that mean? What's that? Oh yeah, they could, but they didn't. Yes. That this was a correct answer. It's a 1, it's not a 0, it's a correct answer. And this is how they got supervised training data at scale. Millions of people use this for years because everybody wanted to save 25 cents. And of course, Google ate everybody for breakfast after that. So this is still just speech to text, even now. Now, there are people doing research on things like tone, emotion, sarcasm detection, but these are still in their infancy. What are some of the challenges there? Yeah. Yeah. A lot more variation. Yeah, it's fuzzy. It's a scale, right? Like someone can be so a little bit sarcastic or very sarcastic. Why would it be important to understand things like anger? Yeah, so maybe there could be an app for an autistic person that would show them the emotion of the person they're talking to on the phone. But it's also good for customer service organizations. In fact, there's some that try to look at just the words you say and figure out if you're angry. And they route the angriest callers to their best service. It's smart, right? But it would be even better if they could get that from the lowest level acoustic model. Remember the acoustic model at the bottom that was looking at the raw wave file and the spectrogram? I think that's where most of the emotional data is. Like if someone says, that was a great movie, or oh, that was a great movie. Totally different meaning, exactly the same words. The only reason that we know it's different is because we knew how to interpret all that extra information that's not in the words. But it's definitely in the wave file and that spectrogram thing. It's in there somewhere. Now, neural networks will get us there someday. And the reason neural networks are a good model to use is because they can handle millions of things, billions of little details that are just too cumbersome for humans to worry about or think about. They'll just handle them. If you ever have, yeah, go ahead.
So would you say that AI, like, sure, we need like data, or do you think it's gonna become so efficient that does that make sense?
It does make sense. And the best example, my favorite to talk about, is these big new language models like GPT-3. Who's heard of that? Did I mention it the other day? Yep. So GPT-3 was trained on 1.1 million years of English. And it still makes errors that a 3-year-old would never make. Did I tell you guys the example about the flock and the shepherd? Even a 5-year-old definitely never makes that mistake. But GPT-3 spouted out that nonsense with high confidence. 1.1 million years of English isn't enough. Whatever it's learning, it's definitely learning a model of English, but it's not learning the way we do. If something did learn the way we did, then it could learn with less data. It could learn with 1 year of data. When my daughter was 1, we started saying words back and forth. And by the time she was 2, we're having really good sentences. So if we had a model that learned like humans, we could do it with, a millionth of the data. We will eventually. So we will make models that could be trained on less data, but we'll still use the data because it's there. Now, there's a very controversial figure in natural language processing who said this. Do any of you know the ending to that? There's no data like more data. We just want more. And this guy is one of the forefathers in natural language processing. He went on to start Renaissance hedge fund with Bill Simons maybe. But his name is Robert Mercer. He also started Cambridge Analytica, which you may also know very famously said they could sway elections by using machine learning. Supposedly it swayed the US election and Kenya and a few other countries. I think jury's out as to whether they actually swayed it, but they definitely advertise themselves as swaying. But there's no data like more data. So even if we could train on less data, we would still train on more data, just because we could.
Do you know how the speech recognition works for languages?
Yes,
Better or worse?
worse just because we had less examples to train. Right now, we're still in a situation where, you need 1.1 million years to get to really, really good levels. We have all that in English. We don't have that in other languages. And the low resource languages are the hardest to get. So what they call them low resource languages. One guy who's studying those, his name is Dr. Connor Quinn. McDonough Quinn. And Quinn. He studies low resource languages, and he also studies ways to teach them and pass them on. He was a student of the guy who was, I guess, the world expert on one of the Native American languages, like Passamaquoddy or Micmac, and then that guy died. So now he's the world expert, and he has literally, written the dictionary. It was his job to write the dictionary, and some of his words had no way to write down until he wrote it down. And there are really interesting things in these other languages that do not map nicely onto English. Things like, if you want to form a noun correctly, you have to know if it's alive or not. Or you have to know if it's rod shaped or flat shaped like paper. This would be flat shaped. Or if it's granular shaped like gravel or water. There's one language I know where, at least in one dialect, the verb is different if the subject of the sentence loves the object of the sentence. If they don't love that person, they use a different person. There's all these unique things in other languages that don't map neatly onto English. So if we make a nice, wonderful model that's trained on tons of English, and we want to use a lot of that intelligence in other languages, it actually might work for French, maybe German, Dutch. Works a little bit more poorly on Russian, very poorly on Chinese, very poorly on languages in India, like Hindi, or Bantu languages in Africa. Does that answer your question? All right, if you have to do a project for school or for anything that requires speech to text, Google is pretty good. Red is actually even better, REV. And I think they're even cheaper than Google. All right, let's talk about accuracy. Accuracy, very simply, is the number of correct answers out of all the answers, right? That seems pretty simple. Are there times when that's actually not a great measure?
When the correct answer is binary, maybe, so there can be a range of outputs, it could be.
Yep. Yep. So let's talk about some of the solutions other people have thought of to find the right way to measure your model's output. Actually, let's talk about search. Let's say you have a model that you can tell, I want to find this kind of thing, bring me back this kind of thing. Let's pretend it's a cancer diagnosing program. So it's going to go out and look at all the scans that certain hospitals taken, look at all the tumors, and automatically determine which ones are cancerous and which ones, are just benign, we don't need to worry about. So in a sense, it's like a search feature, right? And I'll use red for scans with cancer and blue for not. Okay, so we have a whole bunch of these. There's some are cancerous, the red, and some are not. And you send out a program to go search and find just the cancerous ones, bring you back all the cancerous ones and just the cancerous ones, like the whole truth and nothing but the truth, that kind of thing. And it's not perfect. So it goes and gets everything inside that circle. Now, where they are on the board is it's just an example. Don't read too much into that. What we're going to do is analyze the results here. Now, if I were to just look at accuracy, I would say, out of these, which of them are correct answers? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 correct answers, and probably like 16 in there, 17. So it's, more than half correct. That's nice. We have accuracy wouldn't be telling us anything about this. It doesn't give us the whole picture. So people came up with an F1 score, and I'll get to that in a second. But when you look at the slides later, remind yourself of what we talked about. And think about, you have, this one, they're very separated. You have true positives, which are the ones that are positive examples, or in this case, cancer. And you did bring them back. But these are the false negatives. By negative, it means you did not bring it back. And that was actually the wrong thing to do. You should have brought this back in your results. You should have brought this, but you didn't. Now these ones, you brought them in your results. These are like these blue ones in here. Brought these ones in your results, but you should not have. So you said they were positive, but not. So they're false positives. And then the last set is true negatives. So this one, you should not have brought it back in your result, and you did. Good job. You said it was negative, and yes, it's true negative. So we're going to use those terms a bunch of times in this course, and you might need to use them in the comments in your homework, things like that. So false negative, this red example here, a true positive, a false positive, and a true negative. But when people refer to these, they usually use FN to be the number of false negatives. So like in this example in the slide, how many true positives are there? 5, right? So TP will be 5. That's example. So how many of the retrieved items are relevant to what we're looking for? We call that the precision. And I might just write the letter P, capital for that. So precision is that part of the circle over the whole circle. Means the correct part over the entire result I brought back. So if I have a high precision, then everything I'm telling you is going to be true. It's going to be actual result. I may be missing stuff. That's not covered. But at least what I tell you is cancers. This is you need to look at. Recall is not the opposite, but it's another part of the same picture. Out of all the things I should have brought back, how much did I bring back? So out of all the cancerous cases, how many of them did I actually uncover? When do you want really high precision? Give me a case, a real world example where precision is really the only thing or even the number one thing. You don't really care about recall as much. Maybe you care about recall precision is the number one. Diagnostics, okay, like Ford's disease. But if you miss cancer cases, it's still pretty bad, right? That would actually be maybe a scenario for high recall. High recall means you want to get back every case that might be troublesome. So if you have someone who doesn't have cancer, they just have a whole bunch of benign tumors, you still want someone to look at it, right? So that's actually a case for high recall. How about stopping terrorists in the airport? Is that high recall or high precision? Recall. If you stop someone who's not a terrorist and you delay them 5 to 10 minutes, that's not a big deal. But if you accidentally let in a terrorist, that is a big deal. And this is something that friends of mine have worked on before. So did we talk about the Boston bomber last week? Exactly that scenario. Okay. How about the death penalty for murder? Do you consider mostly recall or precision? Precision. It would be preferable in the law's eyes to let a murderer go free than to kill an innocent. We need to have top precision. Now, most real world cases you guys interact with, they won't be skewed toward precision or recall. So how do we balance? And just to give you a hint, the F1 score we'll be looking at the perfect balance between precision and recall. So it is some function, right? Some function of recall and precision. So F1 is a way to balance these. It's not the only way. It's just something that someone smart, people who may be dead now, came up with, some dead mathematicians. And they worked well enough, so we all use it. But let's just brainstorm a little here. This function, do we want it to go up when recall goes up, or go down? How about for precision? We want to go up, precision go down. Typically, what's a good way to have a score go from 0 to 100, negative infinity, positive infinity? What do you think? 0 to 1. Just because it's really easy to handle, and it fits in with a lot of other methods. So what people came up with was this, and it's very easy. 1 over the recall plus 1 over the precision. Now, since it's 1 over something, but it's in the denominator, then this thing goes higher when the recall goes up, and it goes higher when the precision goes up. And it's a maximum of 1. This is the perfect balance. Now, if you go to the Wikipedia page, it's actually named F score. You can go there, you can see that F1 is not the only option. We also have F.5, F2, we have F4, F.1, whatever, F, anything you want. And when you change that number, you slide it. You can favor precision or recall. And maybe you're in a scenario where you don't want to cut it all the way to precision or all the way to recall. Maybe it's somewhere in between. So you would tune that to fit your scenario. There's still something major missing. Let's look at it a little more close. Remember, precision is true positive over true positive plus false positive. And recall is true positive over true positive plus false negative. These numbers are all great and everything, it's very useful, this has been the standard for decades, but there was someone who wrote a paper like, 10, 15 years ago, and almost no one paid attention, but it was actually a really good paper. But he noticed that these have a lot of focus on one thing and not enough on something else. The negatives. There's almost no mention of the negatives here. How could we fix that? Yes. And I'm going to backtrack a little. I don't want to confuse you guys. Some people, when they write the inverse of something, they put with a -1 the exponent. This actually is just 1 over this. I'm not saying that -1 means inverse. In this case, I'm just going to write the word inverse. So the inverse precision, Tn over Tn plus Fn. Inverse recall, Tn over Tn plus Fp. It's the same thing, but focus on the negatives instead of the positives. Almost no one uses this, so I'm just telling you this for your edification. Any job you take, they may not have even heard of this, they will focus on the normal F1. But what some people do is they combine this with the normal one, and they call it informativeness and markedness. And so it's kind of a balance. And if you ever care and you look up the paper, then you can find more about that. I just found someone's credit card on the desk. If you lost a credit card, come see me after class. Okay. So F1 is fine for your homework. When you look at the results of your dumb predictor, you can just do accuracy and F1, or maybe you can report it as precision and recall. All of those are acceptable. You don't have to go to informativeness and markedness, but you could if you want, or inverse precision recall.
Could you explain the like how we do different shapes for like precision recall? I mean, like
Yeah.
in the scenarios you gave me.
Yeah. So let's talk about the airport. People coming in, are they terrorists or not?
Right.
If your system, 99% of the time, it's giving you, if it tells you it's a terrorist, it's a terrorist. Then it has a 0.99 precision. Recall is, let's say 100 terrorists walk through, and for 99 of them, it actually identifies them as a terrorist. Then it has 0.99 recall. Recall is out of how many, all of the things that are out there, cancer, whatever, how many of them do you get back? And precision is, of the things you get back, how accurate are they?
Okay. And you sort of mentioned like that we can control that precision recall, right? Wouldn't you say like that adds like bias to it?
Yeah, and interesting, there's always bias. Now, there's 2 ways that you can play with this. One way is if instead of this, you add some factors that are multiplying in the denominator here. And you can look up the Wikipedia page on F-score if you care enough to do that. That's extra credit though. But that's one way you can play with this. The other way you can play with this is you can make your model want to do one more than the other. And that'll be more complex. It depends on the model. We can talk about that later in the semester. You can't really do that for like simple things like linear models. That doesn't really make sense there, but we will get there eventually.
So if you want like a low bias, would you say like to have more like recall or precision?
A low bias F1, have a balance.
Okay.
That's in a sense no bias.
Right.
In that sense. Bias can be used, there's other terms for bias in statistics. Statistics sometimes will determine what estimator you should use. And a funny example is going from 2 to 3 distributions. If you have 2 distributions and you take a sample from one and a sample from the other, then the best overall sample estimation is going to be like, I'm going to take in a sense, the average. But once you go to 3 different distributions, then you have to use something else. I don't want to get into this too much right now, but if anyone is interested in more information, I can send out a fun video on that. Okay. This is the confusion matrix. This is something else that I encourage you to include in your output. And it's probably fun and easy to code for yourself, but after you do that or later in the course, I don't mind if you use the one in scikit-learn. Scikit-learn, sklearn, same thing. We have a model, and it's predicting whether or not someone has cancer or not. Sometimes it's right, sometimes it's wrong. This is kind of everything we need to see. This is better than just an F1 score, better than just an accuracy score, better than just precision, better than just recall. It's kind of everything, right? So where are the true positives on this graph? How many true positives are there? Someone raised their hand. 6. Yep. And how many false negatives? 2. A negative would say, I'm saying they don't have cancer, but they actually did. Now, what you'll find is this same model applies if you have 3 classes instead of just binary, or 4, or 10, or however many you need. Let's say we had 10 classes and the model was perfect. What would the confusion matrix look like? Yes, they would all be on the diagonal. Would every square in the diagonal have the same number? No, it would just be whatever the truth was, right? So a good confusion matrix will look as much as possible like that. It will have as few as possible outside the diagonal. I would love it if you included this in your output. Any questions?
And you don't want us to use the sklearn.
Not really right now. No, I'd rather you kind of make your own first so you understand. And after you do that once, and I would also like you to compute F1 and your recall and precision on your own.
Or no predictor, it should have only false positives, but theoretically no false negatives, then it's stating what it is. Or
Well, in the cancer one, I mean, you could have, oh, that's right, in your case, that's right, yeah, and yeah, unless it's mostly negative, and then you all negative. Yeah, the number predictors, there is one going to be 0, definitely, in this matrix. At least one of these squares will be 0. All right. So let's look at, in the last 5-10 minutes here, 1 or 2 very simple models. Has anyone heard of k-nearest neighbors? All right. Anyone give me the intuition behind it?
You find 2. Okay, you have a data set and you're given an example. What you do is you find closest matches to that example in the data set, use the data in there to predict what will happen in that example.
All right, so let's do a little game. We're all gonna stand up and have to reorient ourselves, okay? So there, we're gonna have 2 dimensions here. If I'm gonna try to guess if you like a certain kind of music, I want to ask you something, not about music. What are 2 other features that might be? Where are you from? Okay. How many of you are not from Spokane? Okay, that's enough of us. Okay. So let's orient ourselves like the United States, okay? And we'll do Florida over here, Maine over there, Washington State in the corner, and Southern California right here, and I'm in Texas. Where are you from?
Over there.
You have to go over there. You have to go over there. Even if he doesn't have company, it's
What
okay.
they spelled that?
What's that?
What they spelled that?
Mexico? All right, perfect. Where are you from? Belize, perfect. All right. Where are you from?
Malaysia.
Where?
Malaysia.
Malaysia, okay. How about over there? That's as far east as we go, I guess. Where are you from? Cleveland, Ohio. Well, Cleveland, Ohio is our most easterly. Let's spread out a little bit this way to, normalize the data. So Ohio up against the wall, and everybody a little bit this way, as if we're stretching the data. Okay. Now, who wants to say their favorite singer? Okay, you. What's your favorite singer?
I like glass animals. I'll see where it's at.
Glass Animals. Who here has heard of Glass Animals? All right, who here likes Glass Animals? Okay, if I had to predict whether or not you like Glass Animals, looking at K neighbors, let's say K equals 4. The 4 closest people to you are you. Okay, do you like Glass Animals or not? You? You? No? Yes? Look at that, it worked. So more than half of your 4 neighbors like Glass Animals. It was predicted for you. What's another singer?
Elton John.
Elton John. Do you like Elton John?
Love Elton.
Okay. Your 4 nearest neighbors, yes or no? Indifferent. Okay, it worked. All right. How about you? What's one of your favorite singers? Be honest. You don't know? Okay, how about you?
This is the recent one because I haven't considered Greta Van Fleet.
Greta Van Fleet, which to me sounds like Led Zeppelin, Born Again. Okay, do you even know who that is? Do you? No. Do you? Do you? Okay, didn't work for you. Sorry. What's one of your favorite singers?
The Beatles.
The Beatles. Okay, now you're wearing. I'm just gonna imagine almost everyone likes the Beatles. You like the Beatles? Yeah, listen to them. Wait, you? All right. One more. You? Okay, it worked for you. I'm from Boston. And I love opera. Do you? No. You. Okay, it didn't work. One more. Someone from over here. Bruno Mars. Okay, 4 nearest neighbors. That's a good song. Sorry, it didn't work for you. So if it doesn't work for you, maybe you like something that's not popular in our own neighborhood, but on the opposite, very popular internationally. All right. Any other questions or thoughts about this? We'll bring it up again next time, but I think you all have a basic idea of what behavior neighbors is, right? All right, you can all sit down. It's the first simple machine learning model that we're introducing. You want similar things near each other, or people with similar tastes, in our case, to be near each other. Dissimilar ones far. Now, what does it mean to find the optimal K?
Best in the environment. Best number of neighbors around you, is like whether that's 3 neighbors. 4 neighbors.
Or work pretty well for our class, right? Now, in reality, in a system like Spotify, they probably don't use in-ear neighbors anymore, but they might have at some point. And they probably, instead of 4, they probably had e-moves on. And it wasn't on 2 dimensions like the grid of our class, but instead it was probably, 100 dimensions. Anything they knew about it. There are also much more complex ways of doing this we will talk about later, called collaborative filtering. One way to describe it. But for this example, you would just try to find the optimal K such that what? What are you trying to do exactly? Yeah.
Most of the.
To try to guess the right answer, makes sense. Guess if you're going to like a certain kind of music. And find the optimal features. We only looked at, in a sense, 2 dimensions, 2 features. What were our 2 features?
Location.
Yeah.
X and Y.
X and Y, latitude and longitude. Those were our 2 features today. But what are some other features you might use when building a model that's going to predict what music you like? Age, yes. There's a lot of music I like that you guys don't. What else? Male, female. Yeah, so location, age, male, female. Hobbies, yeah.
How long you listen for an average?
Yep. The volume you listen at, I never thought of that. That's really interesting. And yeah, Spotify could probably get that.
Where you listen in the car.
Ah, yeah. Maybe even what time of day you listen. A lot of these companies have access to other things you do when you're not on their app. There are advertising aggregators that break out of the sandbox of the browser. So browsers, when they were first invented, they said, we want to make this safe so that any little widget on the screen that is being run by, Acme.com, whatever company, they will have access to an area in memory or on your disk called cookies. And the memory and the cookies area, it's only accessible to Acme.com. So what Acme.com started to do is they would portion part of their website, part of the infrastructure, maybe even if it doesn't register as a pixel, just behind the scenes, to some third-party aggregator.com. And everybody's on the website. And then everybody benefits. And they all know where you're going all the time. Tracking you. They have a whole bunch of ways to track you. And one of the scariest things to read, which you might want to do someday, is the TikTok URL. What's the URL? Yes. The TikTok URL says that they have the right, I don't know how they get it, but they have the right to access any data on your machine where you install this and your other machines, even if you don't install TikTok.com. That's scary. Well, they'd be asking for that right if they never had access. So, something to ponder. Thank you, everybody. Homework due Thursday. Literally at midnight, but not too nice to finish this for 5. Office hours are right before this time. Every time I come this fast, I'm in my office for an hour beforehand.